Hello, in this recording, I'd like to help you to recap on what we did this past Tuesday, which we continued from the intuitive definition of limit, which we did last week, and we did direct substitution theorem. That's what we did last week. And this past Tuesday, what we did is that we introduced another side limit definition. Okay, the limit on the size. The size basically less than or greater than. So these are the side limit definition. So here I would like to just write down the definition, as you can see, also in the textbook, right? So when we have a limit, right? Suppose we have to start with the intuitive definition of limit. Okay. Start from the intuitive definition of limit. When we have x approaching a, if you think of x is the input, a is also a number that's near, it's a number that doesn't have to be in the domain of f of x, but it is in the same category of input. So sometimes a is qualified to be the input, and sometimes a is not qualified as input. But as we look at x approaching a, x could be approaching a from smaller than a. It could also be approaching a from larger than a. So when a limit exists for the function when x approaching a, this also implies, okay, so if, okay, the definition is satisfied, if we f of x has a limit, okay, has a limit as x approaching a, okay, this is equivalent to say, okay, this is equivalent, equivalent, okay, equivalent to say the following, okay, it says if, so let me make a picture here for you. Okay, so suppose we have a number line, okay, and there's an a here. A is a point where f may or may not be defined. Actually, I should be using red. Okay, I want to be consistent with some scheme I'm about to introduce. Okay, so the input as x approaching a, okay, so we're going to put an up, suppose a is right here. Okay, a is right here. When x approaching a, it could be approaching a from smaller than a. Okay, it could also be approaching a from larger than a. Okay, if this limit exists, what does that mean is that the limit that approaching a from smaller than a, we're going to use this notation, which is a on the shoulder of a, we put a negative sign. This is a little too small. Let me make sure you see the negative sign. Okay. All right. I need to redraw. I think you can see. Okay. So one is when we're approaching a from smaller than a, that limit equals to L. okay? And it could also be that when x is approaching a from larger than a, then we will be using this notation. A on the shoulder, the superscript, is a positive sign. These two notations, meaning the left one is approaching a from smaller than a, and the other one is approaching a from larger than a. Let me redraw the picture so that we can be clear about it. Okay, so in this case, right, we have, this is actually all we did last Tuesday, when we talk about what we have done for calculus. Okay, so we have an A here. A may or may not be in the domain of F. Okay, F may or may not be defined, but that's okay. We are approaching A, if we're approaching A from smaller than A, and the limit is L, that's how we represent it. That's how we express. If A is being approached from, whoops, delete that. Okay. If A is being approached from larger than A, and we are using this notation, we're using this notation. So you need to be very careful because every little symbol is necessary to express that meaning. If you drop the plus sign, that will be different, that will be considered different. Okay. Now, if the limit exists when x approaching A, and this is also equivalent to say that both of these are true at the same time. And the key word here connecting these two is and. So everything we did on Tuesday was about this statement, okay? Which is, I'm going to box it. Oops. We're going to box it. Let me box it. There we go. Okay. Okay. So intuitive definition of limit, right? We have that definition. We covered that definition last week, and we also have direct substitution. But furthermore, we introduce the limits from the sides. Okay. One-sided limit. Okay, we call it one-sided limit. So this is a left side limit, and this is a right side limit. All right. So now let's look at the situation, right? So it's easy to understand if the limit exists, and then the two limits from the sides also exist, and they must be equal to the same limit. Okay, so in this statement, there are some important elements involved. There's some important elements involved. Okay, so if the limit exists, okay, first, if this, typically we will replace is equivalent to say, we will say if and only if. Okay, if and only if means the left-hand side, this piece is imply the other sides are true, and vice versa. Okay, so this means that if the limit exists, not only the side limit exists, the two-sided limit exists, they're also equal. They're also equal. So this implies the side limit exists, that exists. Secondly, the other side limit also exists. Okay. And thirdly, the two must be the same. So that implies these three. That's the three items is implied. Okay, so when this limit exists, not only the limit from the left side exists, the limit from the right exists, and also, thirdly, they are the same. And now the question is, what if the limit does not exist? How many manners could we see that limit does not exist? Okay, so before we get to that, let's take an example that we are familiar with, okay? So example number one. Okay, example number one. We did a lot of examples, right, before, and we did some limits. So I'm going to just look up for those limits. Take this one, for example. Okay, take this one, for example. This one, of course, we have demonstrated limit exists, right? The limit exists. And this function, right, approaching 5, okay, x approaching 5. So if we treat this as a function, certainly we can graph it. We graphed it. Okay. This is a graph of the function. But this function is not defined. It is not defined at 5. So let me show you, because it's not in the domain. And I'm going to, make some changes to the view. The neighborhood is 5 because x approaching 5, right? So I'm going to just make it include 5. I just see what happens. Okay, so this is the function. This is the function. And at 5, the function is not defined. But then you say, hey, there's no dot. Well, we're going to put a dot there. We're going to put a dot there because this function goes, the software is not perfect. Okay, the software has done the reduction for us. So we will have to put the numbers, we'll have to put the dots there. Okay, the software is not perfectly done to graph for us. So we have to, so this is gonna be, I'm gonna put a circle there. Let's see, what point should I get? Okay, it should be 4. Okay, so 5, 4, this should be 4. And there's a circle. Then you may wonder, how do I know? Okay, I will explain to you how I know. Okay, later. Because we already know the limit, right? I would just want to illustrate the situation. So you can see the function, right? This is the function. Okay, I'm going to remove that function, that piece. Okay. You see, this is the function, the input, right? The input x is approaching 5. So here's the 5. 5 is right here. Okay. So I'm going to put the 5 here. The 5 is right here. Okay, that's 5. I'm going to put 5 right there. Okay. So when this limit exists, it means when x approaching 5 from smaller than 5. Okay, so this implies, which also says, okay, which is, how do I put the word? Which is the same as, okay, even though we didn't use these properties here, right? Which is the same as we approach 5 from smaller than 5, this is going to be 4. Okay, and limit as x approaching 5 from larger than 5, the limit is, oopsie, this is a plus sign. Okay. Even though it was not required, because we're not required to express it. But if we are required to say, hey, you got to show me what is the implication in terms of side limit about the same function, then you say, well, if this is 4, then this is true and the other one is true. So this is the application. Of course, approaching 5 from the other side is just like that, right? From larger than 5. Okay, typically in this situation, it is also it's already implied, so you're less likely to be asked that to write down this implication, but it is true. It is true. If we have demonstrated the limit exists, and then the limit on the two-sided limit will also exist, even though most of the time you're not being asked for it. Now, interesting question comes. Okay, so I'm going to clean this up. Is that when we ask the question, what if the limit does not exist? Right? In what situation? What is the opposite of it? Right? What if the limit does not exist? So if limit does not exist, it could be happening in many different ways. Okay, it could be happening in many different ways. Okay, so now the statement we're trying to make, okay, we're going to take this statement here, right? Think about logic, okay? Think about logic. What if the limit does not exist? What if this becomes, right? This is we know it's true. What if this is not? Oops, not equal. What does that imply? Then this will no longer be true, right? Then what would that be is that, or, so this is not L. So what's the logic about that? Right, with the opposite of and is or, right? This is the logic. If A, then B and C. Okay, I don't know if you guys can take this. All right, but try. Okay, it's a simple logic. Okay, I actually didn't cover this in class. If A, then B and C. Okay, but if not A, then what? Right, if limit does not exist, what are the situations? Okay, I'm going to just post this question here for you guys to think about the logic, because this gets a little bit more complicated. I don't think we're ready for it. So I'm not going to spend too much time on this because I did not cover this in class. So let's look at the situation, okay? I'm going to remove this instead. Okay, I'm going to remove that. And we're going to look at the examples we went over in class. Okay, so homework number 3, we've seen a couple of situations that the limit does not exist. Limit does not exist, actually, it happens in different shapes and forms. For example, in this case, right, you see the limit approaching 1 from smaller than 1. So I'm going to use some more screen. Okay, I'm going to use more screen. So let me put it here. I'm going to put this on the side. Okay, I'm going to make this just a little smaller so I can do both screens, so I can type the proper mathematics for you. All right, just 1 second. Just 1 second. Okay. Maybe I can make this just a little bit larger. And then I'm going to share both screens right here. I think this is the better. Okay. When we look at example number 1, this is homework number 3, right? Use the given graph of f to state the value of each expression if exists. So this is the practice for us to practice to express limit from side. Okay, sided limit. Now, for example, from this picture, this is a piecewise function. Okay, this is a piecewise function. What does it mean? Well, you can see the function has 2 pieces. But there's a red circle here, meaning the function is not defined as 0. It is not defined as 0. Okay? And now, and the curve goes, and there's a dot. And this dot is right above 1, meaning that when x equals to 1, and we're going to use this curve. Okay, we can use the point on this curve. Basically, you draw a vertical line. You draw a vertical line across 1, the intersection. Remember vertical line test? Vertical line test, that's vertical line test. So the dot meaning when x equals to 1, the input equals 1, the output is 2. Okay, and the output is not 1 because here is a circle. Vertical, it is a function, that means the vertical line test has to be true. Okay, so now with that said and done, okay, so we're going to look at the limit. Okay, I'm going to copy this so then you see where that example come from. Okay, so this is the homework number 3, right? So we have, of course, a equals to 1. We're approaching 1 from smaller than 1. So we are approaching the number input. Okay, x approaching 1 from smaller than 1. And what is that limit? That limit obviously is 2, right? That limit obviously is 2. The limit on the left exists. But what if we approach the limit from right, from larger than 1? From larger than 1. And that limit, we're approaching it from the right, from larger than 1. Okay, obviously in this case, we use the other rule. And this other rule, the other piece give us a number that's close to 1. But when we approach 1, then, and this is as close as possible to 1, so the limit is going to be 1. Okay, so this is the situation that limit exists on both sides. Sided limit exists, but they're not the same. Okay. Limit from, okay, I think it's easier to write it down than using the words, right? When x approaching 1 from smaller than 1, okay, this limit exists, and the other limit exists as well. Okay, comma. We can say, and this limit both exist. Both exist, but not the same. When you look at this relationship, right, they both exist, but they're not the same. They have to exist and the same in order to say declare the limit exists. And so in this case, we will declare the limit, okay, the limit as x approaching 1 does not exist. Okay, so that's the practice. That's the practice. Okay, so you need to learn how to use a notation. And how do you make your case? How do you make your case? Well, you just basically quote, right? So if this side is not true, then there's no limit. If both are true, when we have a limit. But these not true may show up in different forms, okay? Maybe one of the left limit does not exist. Okay, so that's the study we're doing here. Now let's look at a zero. Let's look at a zero. Okay, let's look at zero. You guys can answer the question number 4, right? Number 4 says f of 1, right? We already did it. F of 1 is equal to 2 because the vertical line we drew, right? Okay, how about f of 0? Well, in this case, f of 0, I should say f is not defined as 0. If f is not defined as 0 because there's just a red circle right there, then, you know, we don't write f of 0. Well, you can say it's undefined. Okay, or you can also say f of 0. Usually this is the first one is much, this piece is preferred. Okay, because typically if a function is not defined as 0, we don't even use this notation. Okay, but if you have to, undefined. Okay, f of 0 is undefined. How about the limit at 0? Right, how about the limit at 0? Well, when we look at 0, right, and we look at limit from left, when x approaching 0, and the limit is about 3. When we approach 0 from right, the limit is also 3, right? So in this case, when we look at the function from both sides, then I'm gonna just also copy this form because I want you to see where it came from. Okay, so when x approaching 0 from smaller than 0, the limit is 3, right? When x approaching 0 from larger than 0, the limit is also 3. And thus, we can say the limit as x approaching 0 is equal to 3. Okay, so you can see we utilize this relationship to speak about it. Okay, so that's one of the homework questions. That's one of the homework questions we went over in class. So let's look at another one. Okay. This other one, I save it for your homework. Okay, it's very similar. So I'm going to leave it for you. And the next thing we did is we did the number 4, and the first one in number 4. And this time we're not given a graph. We can actually graph it if you want. Okay, we can actually graph it. But let's not graphing it for the moment. That we have 3 pieces, right? So let's try to understand this function. So this is a question. This is question number 4. Okay, the first one. And I'm going to write down the function. This function has 3 pieces. We will graph it, but a little bit later. Okay, so we want to first understand how to use this function, functions properly. Oh, don't need that many. So 1 plus x, if x is less than -1, x squared, that's gonna be if -1, oops, -1 less than or equal to x less than 1. And the other one is 2 minus x. If x is larger than equals to 1. Okay, so this is 3 pieces. Okay, you can see the function is defined on the entire number line. However, the function follows different rules. It also satisfies vertical line test. Okay, it should satisfy vertical line test. It should satisfy the definition of function. For each input, there should be exactly 1 output. And you can see the 3 intervals. There's no overlap. Okay, that's typical of when you see this kind of function. All right, so now let's first try to understand this function, right? Suppose I'm gonna give some examples. Suppose I want to do f of -3. How do I evaluate this function? F of -3, the input is -3, and then I will see which interval -3 belongs. -3 belongs x less than -1. Therefore, we're going to use the first rule, which is 1 plus x. X is -3, and the result is -2. Right? If I want to evaluate f of, say, 0, which rule do I use? Well, 0 is between -1 and +1. So I'm going to use the rule in the middle, x squared, right? 0 squared is 0. If I am to evaluate f of, say, 2, well, when input is 2, 2 is larger than 1. Therefore, I'll be using 2 minus 1 as a rule, which is going to be 2 minus 2, 2 minus x. I'm sorry, 2 minus x. So that's going to be 0. Right? For each input, there's exactly 1 output. Now, more questions. Suppose I want to evaluate f of -1. Which rule should I be using? Well, when input is -1, is -1, and this rule is for x less than -1. So now we have is -1. So we're going to use the rule in the middle. So -1 squared. Okay. So if I want to evaluate f of 1, what do I do? Well, I will be looking at 1 is in which interval. 1 is not in this interval. 1 is in this interval. Therefore, I'll be using 2 minus x. X is 1, so 2 minus 1 equals 1. Right? And oftentimes our questions comes at about the border. Okay, at the border. Okay, so now let's try to graph this function, because if you can graph this function properly, and oftentimes it gives you a lot of clue. But if we don't graph the function, it's also not a big deal. Let's see, the software doesn't graph it for me properly. I doubt. There we go. So we got it. So yeah, this software sometimes does do the work. Okay, so this is the function. This is the function. But we need to put the dots and circles in place. Okay, we need to put in the dots and circles in place. I mean, I'm going to make some adjustments about the interval. Yeah, to see if that would do the work. It's not too bad. It's pretty good. But we're missing some stuff, right? These stuff we're missing, we have to look into the definition of the function to put the dots and circles in place. Okay, see from -1 to +1, not including 1, it's a parabola. Less than -1 is a straight line. And greater than or equal to 1, that's a straight line as well. Okay, so now we need to put circles. We need to put circles. Why do we need to put circles? Because on this picture, as x is less than -1, right? At -1, we're using the rule in the middle. So this curve, we should have a circle. Okay, -1, 0. We need to put a little circle right there. Circle. There. What it means is that when x is equal to -1, we cannot use this rule, okay, which is corresponding to this line. We can only use the rule in the middle. And at the same time, we need to put a dot right here, right? So we're going to put a dot, which is 1, 1. We just evaluated that point, right? We just evaluated that point. Oh, wait, sorry. It should be -1. -1, my bad. Okay, we just evaluated that point, remember? When input is -1, the output is +1. So that's the dot. Okay, so when x equals to -1, we're going to use the rule in the middle. That's what it tells us. Greater than, well, at 1, and we're not going to use the rule in the middle. But these 2 points overlap, right? So we're going to put some in, we can put some indicator. 1, 1. Just to so this point is both a circle and a dot. Okay, dot is for the third rule, circle is for the curve. So for that reason, I think we just removed it. We're going to, because at that point they are the same value. They're the same value, right? We just evaluated f of 1 is 1, right? But anyway, so I'm going to remove that circle just to make sure we understand that this is not necessary. Okay, we just use the rule. So you still have to look at the definition of function. And now we're going to answer some of these questions, right? We're going to answer some of these questions. When we answer these questions, right, I'm going to bring the picture right here, right? The first question is when x approaching 0. Oh, wait, x approaching 1, sorry, this one, right? X approaching 1 from smaller than 1. And here's 1, right? 1 is over here, right? 1 is over here. Approaching 1 from smaller than 1, right here. And what is the limit? The limit is 1, right? When x approaching 1 from larger than 1, and then I think that's what you should see from yours, from the, so I'm going to make it bigger. Wait. I'm sorry about these typo. It's actually not a typo. It's just, I need to make an adjustment. This is limit from left to right and to, let me just make it larger so I can see clearly, okay? Oh, first, there's a bunch of -1, I'm sorry. So when we look at x approaching -1 from smaller, -1 from larger, how come we have all these? There we go, this is better. This is better, sorry about that. Okay, you see this is better, now we can see, right? We can see, so one point we're studying is for -1, when x approaching -1, Okay, when x approaching -1. Okay, so here's a -1 from left, right, and -1, right? And what's the value of f of -1? We already did it. So we just look at these three quantities. So the limit, okay, so I'm going to type the limit. Okay, limit as x approaching -1 from smaller than -1. Okay, be careful about this notation. You have to make sure you use these notation properly. If you don't use these notations properly, and then you may subject to a loss of points. Okay, when x approaching -1 from smaller than -1, and the limit is 0, right? But when x is approaching -1 from larger than -1, right? Wait, I have to put it on the shoulder. Okay, not at the same level, I know, okay. When x approaching -1, okay, from larger than -1, and the limit is 1, right? The limit is 1, because we know that we can use the direct substitution property, right? So that's equals to +1. And these two limits both exist and they're not the same. Okay, so what do we say about number 3? It does not exist. Okay, so what is the narrative, right? Doing math and showing work is all about putting together a proper narrative using the language of mathematics. So we can say this limit, the side limit from left, and it's not the same from the side limit from the right. Then you say thus, okay, that the limit removing the side does not exist. You see, the whole time I'm using the language in the statement. Oh, which statement? This statement this is the statement I'm talking about. Okay, this is the statement I'm talking about. Okay, so we're using that statement to illustrate whether the limit exists or the limit does not exist. I hope that helps. Okay. The second one, number 2, is a homework question as well. Okay. Last Tuesday we did not do this one. I will save it for you, so you still have time to work it. But we did work another question in this one, number 5, which I basically copy and paste. I took a picture of these 6 questions. These 6 questions require us to know how to use absolute value. Okay, to know how to use absolute value. And in all of these cases, right, we have to assess the values from the side. Okay, the one we did in 41 is that we want to find limits when x approaching 3, and we have a function in consideration. Okay, so 2x plus the absolute value of x minus 3. How do we handle a function like this? Because x approaching 3, okay, x approaching 3, X could be approaching 3 from smaller than 3. X could also be approaching 3 from larger than 3. If X is smaller than 3, then X minus 3 is, so I'm going to put up an analysis here, okay? You don't have to show work about this analysis. Analysis is the part you don't have to show, but you need to think about, okay? So when X is approaching 3 from smaller than 3, that means X is less than 3, right? If X is less than 3, then the X minus 3 is less than 0, it's negative. If X minus 3 is negative, then the absolute value of X minus 3 is going to be its opposite. Okay? If X is approaching 3 from larger than 3, what does that mean? It means X is larger than 3. If X is larger than 3, then X minus 3 is positive. If X minus 3 is positive, X minus 3 as a positive number, when we take absolute value, is going to be the same as the number, right? We talk about, that absolute value function, which is, there's a narrative, right? The absolute value of any number, okay? If whatever number you have, it could be complicated, it could be simple. Okay, if the quantity, okay, inside the absolute value is greater than or equal to 0, the absolute value of it is going to be the same. If the absolute value, if this number omega is less than 0, it's negative, then the absolute value of omega is going to be its opposite, right? So in our situation, when we have these, so this is the reason why. So this analysis basically tell us that we have to look at these two cases. One case is X minus 3 is a positive. Another case is X minus 3 is negative, right? So that's why we have the following operation, okay? That's why we have these following operation. So when we work it, we're going to basically we're going to use this model. Right? Except, well, in our case, omega is X minus 3. So all the omegas will be replaced by X minus 3, okay? So this omega, we have to insert a parentheses. You can see how easy that is, if you understand that statement, okay? So 2x plus the absolute value of X minus 3 can be branched into the following cases, right? According to that. And of course, you can solve this inequality when X is, I'm going to write another one. Okay, I'm going to write another one just to simplify it. So when X is greater than or equals to 3, or when X is less than 3. Okay, so this one we have two cases. So according to these two cases, and absolute value of X minus 3 is added to 2x. So there will also be two cases. We're adding 2x here, and we're adding 2x here. Does that make sense? I hope that makes sense. Right? X minus 3 is such, and then we added 2x to both sides. So as a result, we're just going to have to simplify these algebraically. Here, we're going to have 3x minus 3. And over here, we're going to have to open up the parentheses that become minus x plus 3, right? And finally, in the simplified form, 2x minus x as x plus 3. So the given function now is made into two pieces. Okay, so to find these limits, right? To find these limits, we have to look at the limit from the side. So naturally, we're going to look at the limit from the side. Okay, from left. Okay, and we're also going to look at the limit from right. Right, so according to these two branches, when x is less than 3, also pay attention to the analysis. Right, you don't need to show the work on analysis, but now you will have to use it, right? You have to use it. Let me make some more space, right? You can see our earlier analysis comes to the picture, right? Along with what we have done to make the function into two pieces, right? So when x is approaching 3 from smaller than 3, which function would apply? This one, right? Less than 3, because when x approaching 3 from smaller than 3, then that's what we use, right? So this case, so we have limits. This time we're going to be taking limit of x plus 3. And how about the other one? Of course, when x is approaching 3 from larger than 3, then we'll be using x greater than equal to 3 case. That's going to be 3x minus 3. You see? Two cases. Now, well, x approaching 3 from smaller than 3, and this is a polynomial, it's a direct substitution. Okay, direct substitution, which must be 3 plus 3 equals to 6. And this other one is also direct substitution because this is a, it's a polynomial, so we can just do direct substitution. So we're going to have 3 times 3 minus 3 equals to 6 as well. So the limit from left and the limit from the right are the same. Hooray! Limit from left is the same as the limit from right. So this is the conclusion statement. I hope everybody make these statements. This is going to add points to your narrative. Even though it may say, oh, do I have to write it over again? It's going to make your narrative very strong. Okay, because you're making a narrative. Okay, so the limit from left exists and the limit from right exists, and they're the same. Then you can say thus, right? This limit when x approaching 3 exists, and it is the same as the two limits from the sides. And so this will be what part, how much work do you show, right? How much work do you show in this case? I would say if you would show well, I think that it will be nice you show these, right? These two lines is helping, okay? So by the last statement we're making here about the conclusion is really applying, we are really applying this principle. So on last Tuesday, that's all we did for calculus. That's all we did for calculus. We're really applying this piece to our situation. Of course, we did some other stuff, right? We did a logarithm review, we did a trig review, and we did a number of other things. You can look for the lectures that I brought some of those lessons to let me share the screen. No, wait, not this one. Okay, so let me share the screen. Just this one. Okay. Just this one. I think I'm gonna make it just a little smaller. We did a lot of other things in terms of review, but I wish to point it to you. I put some recommended lessons for you to watch by moving them to week 3. Okay, I wish you to study absolute value function, which is we just talked about earlier. The properties of absolute value function, root function. I made factoring part 1, factoring part 2 for factoring trinomials, reviewed algebra. For logarithm and trig review. Okay. Please, if you would study these lessons. Oh, wait. Okay, wait. Hold on. I think you probably didn't see the screen. For week number 3, I put absolute value function, property absolute value, root function for you to study, including factoring, review algebra stuff. These are all algebra stuff. Okay, but I mentioned that we reviewed in class logarithm. Okay, because we went over the quiz from last time. So exponential logarithm properties is a very, if you can help it, right, to go study those. Okay. And because the last quiz is about common mistake in logarithm. Okay. I took something from quiz number 2 and quizzed on you. Trig review. If you would look at sign domain range graph, this will be helpful for your trig review. I know there's a lot more, but I'm just giving you a pointer to make the list a little bit shorter. You can only just watch one thing at a time, right? But at least to give you, you get started on reviewing your algebra stuff in order to make this class work. Okay, we will try. Okay, thank you for watching. Until next time.